Hello and welcome to today's lecture for CHY 113. Today we're going to finally start diving into what I would consider some actual chemistry. The first couple of lectures we had to really hit some of the nuts and bolts that we're going to be using, but now we're going to really start getting into some of the meat of our subject. Today our focus is on atomic structure, is looking at the basics of an atom, what makes an atom up, and what are some of the basic properties, because the atom is our basic building block of all matter. And so to have an understanding of matter, we need to know what an atom is all about. We need to know what the structure is of an atom, because it's that structure, which we'll find as we go on through the semester, that really ends up giving matter its properties. And so we have to understand that structure down to some pretty fine details. And so today we're going to take a look at basic atomic structure, protons and electrons and neutrons. We're going to look at some definitions of things like atomic number and atomic mass, and how that relates to isotopes and atomic weight. And finally, we'll end today with looking at some of the basics of the periodic table, how it is set up, and how some of that relates to some of this atomic structure. Some of that we'll get into much more detail when we discuss electron structure in more detail later on, but we will start to delve into it a little bit today. The rest of the chapter outline, molecules and compounds, ionic compounds, and so on, will be the focus of our next lecture. So today we're going through part 2.5 through the periodic table. And so most of you probably know just from your previous science classes that atoms are composed of smaller subatomic particles. Some of those particles are charged, either positive or negative, and some of those particles are neutral, without any charge. And it's this electrical nature of the atom. It's the fact that there are some of these charges involved, which was crucial to discovering this subatomic structure. The fact that electrons have a negative charge is really what allowed them to be discovered in the first place. We're not going to get into some of the discovery of these subatomic particles for the purposes of this class. It goes a little bit deeper than what we have time to focus on here. But I really would encourage you to look into it. To me, those are some great stories of science. J.J. Thomson using cathode ray tubes in order to discover the electron. Ernest Rutherford setting up what is, in my opinion, one of the most beautiful scientific experiments of all time with the gold foil experiment and discovering the nucleus of an atom, doing that. Later on, Rutherford then went further on to discover the proton. And there's just some really fascinating work that went on discovering these subatomic particles. So something, again, that if you have any interest at all outside the class, I would really encourage you to look into those stories. Really, really great science going on there. But back to the atom. And so through a lot of this as well, we have to remember some of the basic laws of what we call electrostatic attraction. And again, most of this is pretty intuitive and things that you know. Like charges will repel each other. Two positive charges start to come near each other. Those positive charges are going to repel. Opposite charges attract. Positives and negatives will attract each other. And these laws of electrostatic attraction really sort of govern how the atom is set up as well. We'll see how that works as we go on. And so here's our basic structure of an atom. We have our nucleus here in the center. Nucleus contains our positively charged protons and our neutral neutrons without any charge. And then we have what we call an electron cloud, basically all the electrons floating around outside the atom, or outside of the nucleus. It's important to note that nearly all of the mass is located here in the nucleus. We can see what the relative masses look like here. Protons and neutrons essentially have pretty much an equal mass, and we set that in a relative sense equal to 1 atomic mass unit. Electrons, on the other hand, 0.0005 units. And so much, much, much smaller. For all practical purposes, we basically consider electrons to be massless. And so nearly all of the mass is located here in our nucleus. Nearly all of the space, however, is taken up by the electrons outside. The nucleus is very small, very dense compared to the rest of the atom. And so again, though, to recap, positively charged protons and neutral neutrons here in our nucleus, and our negatively charged electrons on the outside. And this pretty much sums up a lot of what I just said right here. And so atoms, as they exist in their sort of their neutral state, are neutral. The numbers of protons will equal the number of electrons, and we'll see how to determine those numbers in just a minute. But this is important to note for us, that atoms by themselves are neutral with an equal number of protons and electrons. Later on, when we start to discuss ions, we'll see cases where that is not the case, where we have a differing number of those. But for now, we're going to say that we've got an equal number of protons and electrons in the atom. The atomic mass, like I said, nearly all of the mass is located in the nucleus. And so we consider the atomic mass to be the mass of the protons plus the neutrons. And we can determine the number of neutrons from this mass, and we'll see how to do that. Like I said, the atom itself is really, most of the volume is taken up by the electrons, or the space where the electrons reside, rather. We have our protons and our neutrons in the nucleus. The number of electrons equal to the number of protons, and electrons are in this space outside the nucleus. To put this into perspective a little bit with the sort of the sizes and the space that we're talking about, the analogy that I've heard that I really like is if you consider some huge sports dome, think about something like the Houston Astrodome. The entire dome, that entire sports dome, is analogous to the atom. So that dome is the entire atom. The nucleus would be roughly the size of a baseball hanging in the center of that dome. The rest of all of that space is where the electrons are zipping around. And so then we can consider all that space where the electrons are. Now let's think about a couple of mosquitoes flying around in there. So those mosquitoes have that whole space, have that whole dome to fly around in. Those mosquitoes are the electrons. And so, like I said, essentially, a mosquito is essentially massless in comparison to something like a baseball. And we have all that space. That's the space where the mosquitoes, where the electrons are all flying around. And so that's what we mean if you hear, or like we're saying here, that the atom is mostly empty space. That's really what we mean, is that when we look at the size of an entire atom, the nucleus is a tiny little spot just in the center of that, but that's where pretty much all of the mass is. And then our electrons are all zipping around in a huge space in comparison, a huge space outside. And so that's our basic structure of an atom. Our protons and our neutrons in the middle, and our electrons zipping around in a huge area outside of that. So we have to define a couple of key terms here. The first is what we call atomic number, or Z. The atomic number is equal to the number of protons in the nucleus. This is the absolute defining aspect of a type of atom. And so we see an example here of aluminum. We'll worry about this atomic mass down here in a few minutes. Don't worry about that now. For now, let's focus right here on the atomic number. Z equals 13 for aluminum. That is what makes aluminum aluminum. If an atom has 13 protons in its nucleus, it is aluminum. That is the very definition of an aluminum atom. If there's something that doesn't have 13 protons, it's not aluminum. And so every single atom in the universe that has 13 protons is aluminum. That's the definition of it. And this atomic number is one of the key things that we find on the periodic table. And so here's our periodic table here. And so we can see aluminum right here. And this number here in the upper left, 13, there's our atomic number. And we can see that that's in fact, one of the ways the periodic table is set up, with hydrogen here, atomic number 1, 1 proton. Then over to helium, 2 protons, lithium with 3, beryllium with 4, and so on. And so the periodic table is set up in order of increasing atomic number until we get all the way up to the largest one that we've discovered at this point, with atomic number of 118. And so that's a very key number to know. We're going to be using that number for quite a bit of things when we discuss atomic structure, when we discuss ions and charges later on. That atomic number is going to be important for us. So again, it is the defining aspect of an element. If an element has 20 protons in its nucleus, it's calcium. If an element has 47 protons in its nucleus, it's silver, and so on. And so that atomic number defines what an element is. I cannot stress that enough, that the atomic number is the defining definition of an element. The other thing that we do find in each box in the periodic table is the elemental symbol, Al in the case of aluminum. Now the atomic numbers, when we're looking at the periodic table, the atomic numbers and masses and symbols and all that, and then the names that go with it, it's nothing that you have to memorize for the course. I'm not going to give you test questions that say, for instance, what is the symbol for the elemental symbol of iron? You know, I'm not going to ask you things like that. You will end up memorizing some of it just from sheer usage. Probably by the end even of this lecture, you're going to have the fact that carbon has an atomic number of 6 memorized, just because we're going to use it as an example. But so you'll never have to memorize things in this per se. What I will teach you is how to use it, how to use the periodic table as a tool to find the information that we're looking for. And you will be allowed to use a periodic table on every assessment that you take. You can always have a periodic table sitting in front of you with any exam that you take in this course. Okay. And so moving on. We also have atomic weight. And actually, I'm going to come back to the atomic weight later on. We're not going to focus on it that much right now. Let me come back to this in a little bit. Mass number is the next concept that I really want to talk about. The mass number is equal to the number of protons plus the number of neutrons in a nucleus. And so we often use this type of notation here with the elemental symbol. So the element symbol, whatever that element might be, our atomic number as a subscript down to the left, and our mass number as a superscript to the right. And we assign the letter A to mass number. So again, it's just like atomic number being Z. We say Z equals 6 for carbon. Mass number equals A. So A equals 14 for the isotope carbon-14. And we'll talk about isotopes here in a little bit. You won't always see the atomic number. You won't always see Z in this sort of notation because we don't necessarily need it. Remember, as long as we have the elemental symbol, as long as we know what element it is that we're working with, we can always look that up. If we're working with carbon, we can see that we can look on the periodic table and see that Z equals 6. If we're working with copper, we can look on the periodic table and see that Z equals 29. And so you won't always be provided with that information when you're looking at this notation, but just know that you will be able to look it up on the periodic table. And so, for instance, carbon-12, and that's what this notation means here. C for carbon, -12. So we're talking about what we call a carbon-12 atom. Means that our mass number of carbon-12 is 12. Now we know that the atomic number of carbon is 6. That's never going to change. That's what makes carbon carbon. And so if the atomic number is 6 and our mass number is 12, remembering that mass number is protons plus neutrons, that means in carbon-12, we must have 6 neutrons. And so we would say that it has a mass of 12 atomic units. And we'll talk about that mass again more in a little bit. There's also a different type of carbon with a mass number of 13. Carbon-13 is still going to have 6 protons. It's still carbon. And that is such an important note to make, that it is still carbon. Every carbon atom, the defining aspect of carbon is that it has 6 protons. And so that means that carbon-13 must have 7 neutrons. And so here we have these 2 different types of carbon then. We have a type of carbon, carbon-12, that has 6 neutrons. Another type of carbon, carbon-13, that has 7 neutrons. And so these are 2 different types of carbon. They're still carbon, so they both have 6 protons, but they have differing numbers of neutrons. And so elements that are the same element but with different numbers of neutrons are called isotopes of each other. And so carbon-12 and carbon-13 are 2 different isotopes of carbon. Let's just look at another example here. So we have fluorine. Our atomic symbol is F for fluorine. We look on the periodic table. We see that the atomic number of fluorine is 9. That means there are 9 protons in a fluorine nucleus. That means that our number of electrons is also going to be 9. Because when we're talking about a neutral atom, we have the same number of protons as we do electrons. Our number of negative charges from the electrons has to balance out our number of negative positive charges from the protons. And so for now, pretty much just for today, we're going to say that the number of protons is going to be always equal to the number of electrons. And it is always equal when we're talking about a neutral atom. But we won't always be talking about neutral atoms. So just keep that in the back of your head. And so for this particular fluorine isotope, the mass number equals 19. And so again, if we know that there are 9 protons, that means that our 19, our mass number, minus those 9 protons, means that fluorine 19 has 10 neutrons in the nucleus. And this is how we might symbolize that. So we have our elemental symbol, we have fluorine, F. We have our mass number here of 19 and our atomic number of 9. Remember that the mass number is our protons plus our neutrons, and the atomic number is our number of protons. And so we get fluorine 19. 9 protons and 10 neutrons. And 9 electrons. So the existence of isotopes and the fact that isotopes exist means that all atoms of an element are not exactly the same. All atoms of the same element will absolutely have the same number of protons in the nucleus. Once again, remember, that's what makes an atom the type of atom that it is, the number of protons. And so all isotopes of fluorine that we were just looking at are going to have 9 protons in the nucleus. That's what makes it fluorine. All isotopes of iron are going to have 26 protons in the nucleus. That's what makes it iron, and so forth. Every single isotope of gold is going to have 79 protons in the nucleus. All different isotopes of uranium will have 92 protons in the nucleus, and so forth. Even though there are, in fact, several different isotopes of uranium that exist, they will all have 92 protons in the nucleus. Where they are going to differ is the number of neutrons in the nucleus. They will all have different mass numbers, which means they will all have a differing number of neutrons. And so for any given element, X, any just generic element, once again, our symbology here is our elemental symbol with our mass number as a superscript to the left, and our atomic number, which may or may not be written depending on just depending on if it's there or not. But that's equal to our atomic number, our number of protons in the nucleus. And remember that the atomic number Z, that's our number of protons, and the mass number is our protons plus our neutrons. And so here's just another example here. Hydrogen has 3 naturally occurring isotopes, and they all do have different names in this case. We have hydrogen 1. And so if we look up hydrogen on the periodic table, it's the very first element. It's got an atomic number of 1, so 1 proton in there. And so hydrogen 1 with a mass number of 1. Mass number is 1 and the atomic number is 1. That means that hydrogen 1 has no neutrons. There's just a proton there in the nucleus, and we call that protium. Hydrogen 2, now we still have 1 proton. It's still hydrogen, so it's still just 1 proton in there. But now we have 1 neutron. And so we have what we call deuterium. And then hydrogen 3 has 1 proton still, but now we've got 2 neutrons in there, so a mass number of 3. And that's called tritium. So let's check out this question. And so which of the following is true? So boron 10 has 10 electrons, boron 11 has 11 neutrons, boron 10 has 5 electrons, or boron 11 has 11 protons. And so again, when we have these little concept checks through these video lectures, I would recommend that you pause the video now, figure this out, and see if you can come up with an answer. Okay, hopefully you're back. And so to figure this out, the first thing that I would do is I would look on the periodic table. That's going to be your first move for many types of questions when you're looking at atomic structure. And so we're looking at boron. And so we check our periodic table, and we see that boron has an atomic number of 5. So we know that there are going to be 5 protons in boron's nucleus. And so let's just sort of start keeping track of this. So we're looking here at boron. We just looked on the periodic table, and we saw that Z equals 5. So we have 5 protons in the nucleus of boron. So let's start just looking through our options here. And so boron 10, so we know we're going to have 5 protons in there because it's still boron. Boron 10 would also then have 5 electrons, and that E with a negative, that just is a symbology for electrons. And so boron 10 would have 5 electrons in it. So we know A can't be right. So let's look at B. Boron 11. Still going to have its 5 protons in there. Now boron 11, so our mass number is 11. And so our protons plus our neutrons will equal 11. We know that we have 5 protons in there. And so 5 plus our number of neutrons has to equal 11. So we know boron 11 has to have 6 neutrons. So B can't be right. And so C, now we're looking at boron 10. Again, we know we're going to have 5 protons in there since it is boron. And since it is a neutral atom, that means we're also going to have 5 electrons. So C looks to be correct. Well, let's just check D out at the same time. Boron 11 5 protons. And so, 5 protons, meaning that we're also going to have 5 electrons in there. And so boron 11 obviously can't have 11 protons. And so D is incorrect. And so C is our answer. Hopefully that is the answer you gave. So now another one. How are chlorine 37 and calcium 40 similar to each other? So again, pause the video, try to go through an analysis similar to what we just did and see if you can come up with how these two isotopes are similar. And we're back. So I would go through the same sort of analysis that we just did, but now we're going to look at our number of protons, electrons, and neutrons for each of these different isotopes. And so let's just set up a little table here maybe. So first we're going to have chlorine-37. We also have calcium-40. And so let's look for each of these at our number of protons, our number of neutrons, and our number of electrons. And so chlorine-37, let's look on our periodic table. Chlorine is going to have 17 protons. Its atomic number is 17. While we're here on the periodic table, we'll also just look at our protons for calcium. Calcium is going to have 20 protons. Atomic number is 20. And so since we're talking about neutral atoms, that means that we can also fill in here we go. It means we can also fill in our electrons easily. They're going to be equal. So 17 electrons for chlorine-37 and 20 electrons for calcium-40. And so now let's look at our number of neutrons. So remember that our mass number, 37 in the case of this chlorine and 40 in the case of this calcium, our mass numbers are equal to our protons plus our neutrons. And so 37 is going to equal 17 plus our number of neutrons. And so our number of neutrons in chlorine-37 is going to be 20. And for the case of our calcium isotope, 40, our mass number, is going to equal 20 plus the number of neutrons. And so we also have 20 neutrons in calcium-40. And so that brings us to an answer of C, is the only one that is correct here. Our number of protons are obviously different. Our number of electrons are obviously different. But our number of neutrons is the same between these two isotopes. And so hopefully you came up with an answer of C. If not, then I hope that answer makes sense to you now that we've gone through it. Okay. We can use something that we call a mass spectrometer, a fairly complicated, usually pretty expensive instruments. But mass spectrometers can be used to actually separate different isotopes from each other. And using those, we can determine the masses of isotopes and their abundance by using mass spectrometry. And so by abundance, what we mean by that is that the amount of isotopes that exist are going to be different for every different element. And so for instance, boron has two primary isotopes, boron 10 and boron 11. And we can see here by the graph, and so if we give a percentage of relative abundance of 100 to boron 11, then that means the relative abundance, of boron 10 is only 25%. And so much more of the boron that exists is the isotope boron 11. For chlorine, we can see that the isotope that's in a much higher abundance is chlorine-35. And so those two primary isotopes of chlorine exist. And so each of those are stable. And so any of the chlorine that you might find out in the world, some of it might be chlorine-35, some of it might be chlorine-37, but much more of it is going to be chlorine-35. And so let's look at how we're going to use some of that information. And so first of all, the way that we calculate a percent abundance is if we just take, for instance, if we have, if we have a sample of a certain element, then we take the number of atoms of an individual isotope. So if we're looking at chlorine and we want to calculate how much of it is chlorine 35 versus how much is chlorine 37, then we take a sample of chlorine, and however many atoms of chlorine 35 we have in there, divided by our total of chlorine atoms, and then multiplied by 100 to convert that to a percent, leads us to the percent of chlorine that is chlorine 35, and so on. And so percent abundance is simply just when we take a sample of any element, how much of it, what percent of it is one isotope and what percent of it is another isotope. Now, there are definitely some elements that have more than 2 stable isotopes. Some of them could have upwards of 4 or 5 different stable isotopes that will all have different percent abundances. And so that's just something to keep in mind as we move on. But we calculate that, but the idea is the same. That percent abundance for any of those isotopes will simply be the percentage of all of the atoms that are that particular isotope. So let's look at an example now, thinking of what we call the atomic weight or the atomic mass. Atomic mass, for now, we're going to think of atomic mass just in these sort of ambiguous terms of atomic mass units. Atomic mass units does have a real definition, but honestly, for our purposes for right now, that definition doesn't mean much. We're going to attach much more definition to that in a couple weeks. But for now, we're just going to think of atomic mass in these ambiguous terms of atomic mass units, and we're just going to think of it as how much does the atom weigh. When we look on the periodic table, and so let's take a look again at the periodic table. I'm sorry, this is maybe a little bit blurry. I don't know how well you can see it. There we go, that helps a little bit. So when we look here at the periodic table, blow that up a little. And so something like, well, like chlorine. So we'll stick with our chlorine example here. This 35.453, that's the atomic mass, that's the atomic weight of chlorine. That number, though, is a blended average that takes into account the abundance of chlorine that is chlorine 35 and the abundance of chlorine that is chlorine 37. Because some of the chlorine that exists is going to be chlorine 35 and some is chlorine 37. And chlorine 35 and chlorine 37 are going to have different masses because they do have that differing number of isotopes. And so the atomic mass, this 35.453, takes that into account. It takes into account that some of the chlorine that we find is chlorine 35 and some of it is chlorine 37. And so what we need to look at then is how we actually calculate this number. How do we come up with this 35.453? And so the way we do that, when we find the atomic weight, what we have to do is take the percent abundance of isotope 1, and then we divide that by 100. So percent abundance is usually given, as the name implies, in a percentage. And then we just divide it by 100 to remove the percent sort of from the situation. And so you'll have a decimal number at that point, 0 something. And so then you take that abundance of the isotope and multiply it by the mass of the isotope. And then you do the same with the other isotope. And so in the case of chlorine 37, or in the case of chlorine, we would take the abundance of chlorine 35, the percent abundance of chlorine 35, divide that by 100. We would multiply it by the mass of chlorine 35. And then we would take the percent abundance of chlorine 37, divide that by 100, and multiply it by the mass of chlorine 37. And then we add them up. And in cases where you have more than 2 stable isotopes, you just do this for all the stable isotopes that you have, and you add them all up. So let's look at an example. And so chlorine, as it occurs naturally, has a 75.53% abundance of chlorine 35. And so again, that means that 75.53% of all chlorine that exists on Earth will be chlorine 35, which has a mass of has a mass of 34.96885 atomic mass units. And so here's our mass of chlorine 35. The remaining chlorine, 24.47%, is chlorine 37, which has a mass of 36.96590 units. And so we want to use this information. We want to use the percent abundance and the mass of each isotope to calculate what the average atomic mass is, to calculate what we call our blended atomic mass. And here's how we would do that. So we take our mass of a chlorine atom. And so here's chlorine 35 right here. So our mass of chlorine in general, so our average mass of chlorine, is going to equal our mass of chlorine 35. So here's our mass of chlorine 35 times the abundance of chlorine 35. Here's our 75.53 divided by 100 to convert it to a fraction, to convert it to a decimal. And then we add that to our mass of chlorine 37. That's the 36.96590 from the last slide. And then our abundance of chlorine 37. So there's our 24.47 divided by 100. And so we take those numbers, we just do the math of that, and we come up with an average mass of chlorine of 35.45 atomic mass units. And lo and behold, that's what we find on the periodic table. And so we just take, again, to recap that, we take the mass of each isotope, multiply that by the abundance of that isotope, making sure to convert that from percent down to a decimal, just divide that percent by 100. And then for every isotope of that atom, you add them up. Okay, let's look at another example. Let's take a peek at neon. And so what I have here are the three different stable isotopes of neon: neon 20, neon 21, and neon 22. Neon 20 is a percent abundance of 90.48. Neon 21, a percent abundance of 0.27%. And neon 22, 9.25%. And I've written down all the different masses of the different isotopes here. And so what we want to do is to calculate the average atomic mass of neon. And so we're just going to take all three percent abundances, multiply that by the masses, and we're going to add them up. And so our average mass then is going to equal, so we're going to, again, take our 90.48, divide that by 100, and get 0.9048, and multiply that by our mass of neon 20. Then we're going to add that to the same thing for neon 21. We'll divide our 0.27 by 100, multiply that, and then our final factor for neon 22, times the mass of neon 22. Then we put this all into a calculator and we add it up, and we get 20.180 atomic mass units. And so let's check the periodic table. Neon, 20.180. And so that's all there is to it. All you do is again, take the abundance of each, multiply that by the mass of each, and then add them up. Let's look at a somewhat more complicated example, though, because sometimes what you're going to be given is information like this. So in the case of copper, we have two stable isotopes, copper 63, which has a mass as shown, and copper 65 with that mass shown. We know the average the average atomic mass from the periodic table is 63.546. From this information, what we want to do now is to calculate the percent abundance of each of copper's stable isotopes. And so let's take a peek at the actual equation. Make this really small over here so we have lots of room to see our calculation. There we go. And so if we remember what our calculation looks like, our average mass is going to equal our mass of copper 63 times our abundance of copper 63 plus our mass of copper 65 times our abundance of copper 65. And so let's start putting in some of the numbers here that we know. From the periodic table, we know that copper does have an average mass of 63.546. And from the information given in our problem, we know that copper 63 has a mass of 92960. I'm going to go ahead and leave this blank for now, our copper 63 abundance. That's what we're looking for. We know that our copper 65 has a mass of 64.92779, and then times our percent abundance of copper 65. And so what we're going to do now is we're just going to put X in here for our abundance of copper 63. That's one of the factors that we're looking for. Now, if we think about this abundance, the percent abundance of copper 63 plus the percent abundance of copper 65 has to equal 100%, because we're told that copper only has these two stable isotopes. And so all the copper that exists out there in the world in its stable form is either copper 63 or copper 65. And so the abundances, the percent abundances, have to equal 100%. And so if we look at what our calculation was earlier, we always took that percent abundance and divided it by 100. And so 100 divided by 100 is going to equal 1. That means that the abundance of copper 65 is going to be 1 minus X. So think of it, if we're thinking in terms of percentages, 100%, which is all of the copper, 100% minus the percent abundance of copper 63 is going to equal our percent abundance of copper 65. And so that's 1 minus X. Now we just have to algebra this. And yes, algebra in this case is absolutely a verb. And so we're going to start algebraing. And so we're going to first just keep our 63.546. Now we're just going to distribute this X through. We'll get 62.92960X plus, now we're just going to, again, we're just going to do the math of this. We're going to multiply our mass here by 1 minus X. And so if we pull that through, we get 64.92779, minus, so that's just our number here times 1. And then so minus 64.92779 X. So we're just distributing our X's and our 1 minus X through the equation here. And so now to simplify this, we're going to just subtract 64.92779 from both sides. And we're also just going to simplify our X value here. We'll subtract 62.92960 X minus 64.92779X. And so when we do that, so we subtract our 64.92779 from both sides, we get negative 1.38179 equals, and we've subtracted our x terms from each other here. So we've done that subtraction, and that's going to equal negative 1.99819x. And so now what we can do, again, just more algebra, we're going to go ahead and divide both sides by this negative 1.99819, and that will then get x all by itself. We will have solved for x. And so when we do that math through, we get an x value equal to 0.6915. And that's equal to x. Now let's remember what x was. We set x equal to our abundance of copper 63. And so copper 63 has an abundance of 0.6915, or if we then convert that up to a percent, 69.15%. And we set the abundance of copper 65 at 1 minus x. So 1 minus x is going to equal 0.3084. Or a value of, a percentage of, rather, of 30.84%. And so copper 63 has a percent abundance of 69.15%. Copper 65 has a percent abundance of 30.84%. Now I know, just as a side note, that some of you might be looking at this saying, oh, this should have been a 5 right here, Professor Staples. What happens there is I typically don't round when I leave answers into my calculator. And so I hadn't rounded x off. And so without rounding, it came to 0.3084. So it's just some rounding differences that happen through the course of the calculation, and that is absolutely fine. But as a final check right here, what we can do is we can just take a peek. Again, we know that the percent abundances has to equal 100. 69.15 plus 30.84 gives us 99.99. Again, pretty darn close. That 0.01 is just a difference in rounding, and so that might happen. I encourage you to do final checks like this to make sure that you are in the ballpark. So again, 99.99, that tells us there's a rounding difference somewhere, and that's fine. If you do this check at the end and you come up with 72.4, okay, that's not a rounding error. That's an error made somewhere that you have to go chase down. And so do that quick check at the end just to make sure that things are adding up close to 100. All right, let's talk briefly about the periodic table. And so, like I said, elements are arranged in order of increasing atomic number. And the periodic table was arranged before any sort of electron configurations were even known. And that's one of the things that we'll see when we look at electrons in more detail in a couple of weeks, is that it turns out that there's a lot of information about electron configuration that we can get from the periodic table as well. Properties of elements are what we call periodic. That just means they repeat every so often. And so, for instance, when we look at the noble gases, so we have our noble gases here all the way over onto the right. We have helium. And then 8 elements later, we come to neon. They're both very unreactive elements. 8 elements later, we come to argon. And then we have repeating patterns of 18. 18 elements later, we come to krypton. 18 elements later, we come to xenon, and so forth. And so we have this repeating pattern of properties. So that's what we mean when we say that they are periodic. Dmitry Mendeleev is really the first person who developed what we call the modern periodic table. what he did is really sort of fascinating, is that he started to lay out elements according to their size. And what he found was this, again, this periodic, this repeating pattern of behavior. And so then he started to line those elements up in columns according to those repeating patterns. He was so good that what he did is that when he laid out this table, when he laid out his table, what he found is that there were gaps in there. And so, for instance, his most famous example. So he's laying out his table. And at that point, this element here, germanium, had not been discovered. And so he's laying things out and he's saying, okay, well, we've got aluminum. And so that's going to go here. And then gallium has very, very similar properties. So that's going to go right under aluminum. And then the next element that we knew of after gallium, though, was arsenic. And what he found, though, is that he said arsenic can't go in this spot. Arsenic doesn't have the same properties that silicone does. It doesn't have the same properties as tin. It does have very similar properties, though, to phosphorus and the antimony. So he said arsenic has to go here. And he said that this space here in the periodic table, he said I'm going to leave that blank. That blank space, and he found this in a few other places in the table. He said these blank spaces that I'm leaving, these are elements that we haven't even discovered yet. And so he predicted that these are elements that had to exist for his table to work, for this repeating pattern of properties to be consistent. And he was absolutely right. This is, again, I love this sort of unit in general because there are so many fascinating stories of science, and this is one of them. He found that he was absolutely, definitely right that these were elements that hadn't been discovered. Or actually, I honestly don't remember if he was vindicated and those elements were found before he died or not. But it was found that he was completely right. And he not only predicted they exist, he predicted their properties. And look at how close he was. He predicted an atomic weight of germanium of 72, the actual atomic weight, 72.59. Predicted a density that was really close. Specific heat, which is a property we'll be talking about in a month or two, very close. He didn't actually predict a number for melting point, because that's tough to do. He just said, it's going to be high, and sure enough, it was. And so he was able to predict all these different properties, and he was dead on. And so what he had called it eka-silicone, just meaning that it's going to come under silicone, come after silicone. And later on, it was discovered and called germanium. And so he's sometimes called the father of the modern periodic table, because he was the first to really set things up in this way, and it was brilliant. It really was. And we will be talking much more about the periodic table as we go on and its setup. For just a few basics of it, the periodic table is set up into what we call periods and rows, set up into regions of metals and nonmetals and metalloids. And we have things like halogens, noble gases, and alkali metals, and some of this we'll be getting into much more detail later on. But just some of the basics, groups or families are the vertical columns. So we have group A elements, which are the two columns on the left, and then the columns over here on the right. Then group B, which are these here in the middle. And the numbers, so group 1, group 2, and then usually when we talk about groups 3, 4, 5, 6, 7, and 8, we're talking about these that are also over here in group A. We usually don't talk about group B by assigning them numbers. And so they do have numbers, but honestly, we don't really refer to them as such. So if you hear somebody talking about a group 6 element, then they're talking about elements that are in this column right here. Then we also have periods, which are our horizontal rows. And so periods 1 through 7. And then we have what we call the main group elements, which are our group A elements, and then our transition metals, and then our main group metals, you can see here shaded, and then non-metals and metalloids. And we'll talk a little bit more in detail about those features probably in our next lecture, actually. And so there's just those regions blown up a little bit. And so these are definitely terms that you want to know, and then we'll apply some more terminology to the periodic table later on. But for now, I'm going to leave you with this. This is all for today. Some of the basics just of how the periodic table is set up. And it all does relate. We'll see how it relates later on to the aspects of atomic structure that we've talked about. And so I hope you have enjoyed this lecture as much as I have. It's still, honestly, from on a personal level, really tough to get used to talking at a camera. I really, online was the way that we had to go for this semester, but I miss seeing the audience of people in front of me. But we'll all get used to it. And so if you have any questions, as always, send me an email. Use Piazza. Piazza is a tremendous tool for answering questions, and so feel free to post questions on there, and your classmates might be able to help. But for now, I will see you next time. Here's the part where you stare at me until I am able to get the recording to stop. There we go.